So, good evening. We are a group of 6 people named Aspiring AI Learners and are presenting our group project, which is about the data analysis and machine learning on a PIMA diabetes dataset. It's me, Saima, and I will be starting with the introduction. The PIMA Indians have been researched as they have a high rate on diabetes disease. Our project is based on diabetes prediction. Just to know, diabetes is a chronic metabolic disease that is getting more common across all age groups. High blood glucose levels lead to further health issues, which often then require long-term care. Hence, it would be good to identify the symptoms early to be able to treat diabetes. As we wanted to get data analysis and machine learning experience on real world data and find a purpose in our work to find eventually a solution to pre-diagnose diabetes and save its cost, we analyzed first the data trends and implemented 2 machine learning models and compared these two based on reliability and accuracy. The selection of the dataset is based on personal connections. The presentation is basically split in following parts. I will start with the data description. Maureen will do the exploratory data analysis part. Mohammed will continue with the feature engineering. The model evaluation and performance will be done by UFI. Discussion and interpretation will be done by Joshua, and the conclusion and future directions by Hepsi. So we are starting to talk about the data description, preparation, and cleaning. As I mentioned, we have chosen the PIMA diabetes dataset. That was sourced from Kaggle, and it has 9 features, namely pregnancies, glucose, blood pressure, skin thickness, insulin, BMI, and diabetes pedigree function. Originally, the dataset was published by the National Institute of Diabetes and Digestive Kidney Diseases, but it is just a small selection of data from a larger dataset. The data had to be pre-processed. Initially, there were 768 rows. We as a team decided to remove the rows with the nil values, which were 374 on 3 features: glucose, insulin, and BMI. So at the end, we were left with 394, and the remaining data points with any nil values were replaced with the median. In the next steps, we had to take further steps to do the data cleaning process to analyze and determine what we will have to do for our EDA. Instantly, we discovered all features had skewness, and with the help of box plots, we could see that there were multiple outliers above the upper bound and beyond the lower bound. So we then performed an outlier removal, but due to the skewness of the data, new outliers came apparent. So the thing is, there is still skewness, as most of the data points point towards the fact that the lower the age is, the higher the probability to have no diabetes. So generally with age, the chances to get diabetes increases. But we thought that maybe working with a larger data set would get more accuracy about this. Now I will hand over the presentation to my colleague Maureen. She will talk about the EDA.
The next phase of the project was the exploratory data analysis. The EDA tools engaged were line graph, scatter matrix, and heat map. Our findings from the line graph showed pairwise numerical correlations between the different features, with BMI and skin thickness showing the highest correlation. The scatter matrix reveals that most data points for BMI and skin thickness were clustered around the midpoint, indicating a stronger correlation to diabetes compared to the other features. Furthermore, the heat map indicates strong correlations between diabetes and BMI and skin thickness. The EDA tools informed the team's selection of the features to be used for model training. I'll now hand over to Mohammed for the feature engineering.
So for the feature engineering, we utilized three features. One was diabetes outcome, and the other two were skin thickness and BMI. Skin thickness and BMI were continuous data points, whilst the outcome was a binary data point. We trained logistic regression first, and then predictive probabilities, finally testing for accuracy levels using the TP, TN, FP, and FN figures, meaning true positive, true negative, false positive, and false negative. We then created a decision tree classifier for random forest to start, plotted a decision tree, and then worked on the overfitting by pre-pruning. We then used several decision trees and implemented bagging, then ADA boosting and XG boosting. I'm now going to pass on to Yufei, who's going to talk about model evaluation.
I will share our model evaluation and performance. Logistic regression achieved over 60% accuracy. It's simple and easy to use but sensitive to outliers. Random forest gave 75% accuracy on test data. It handles outliers well but uses more memory and time. In short, both models worked, but tuning could make them better. Thank you. Now let's move the part of discussion and interpretation to my colleague Joshua. Thank you.
The dataset analysis identified strong correlations between diabetes outcomes and features such as body mass index and skin thickness. These findings aligned with established medical research, establishing BMI and fat thickness as significant indicators of diabetes. Our scatter plots, line graphs, and correlation heat map revealed that higher values of these indicators are associated with positive diabetes diagnosis. The presence of outliers detected through box plots and addressed using the interquartile range method underscored the importance of pre-processing for improved model accuracy. However, the skewness in data distribution and emergence of new outliers after these adjustments were made highlights the complexity of working with real-world data sets. The logistic regression model was over 60% accurate, making an effective tool for predicting diabetes based on the factors mentioned. While logistic regression is simple, cheap, and easy to understand, its sensitivity to outliers and assumption of linearity limit its application to more complex data sets. The random forest algorithm outperformed logistic regression with a test set accuracy of 75% and training accuracy of 88%. Its ensemble learning approach, robustness against overfitting, and capacity to handle diverse data types contribute to its performance. However, the computational cost and potential overfitting on noisy data require moderation to optimize results. Alternative methods such as bagging, ADA boost, and XG boost provided additional benchmarks at 58%, 64%, and 66% respectively. While they offer good performance, they fell short of the random forest model, reinforcing its suitability for this data set. Now passing on to Hepsi for the conclusion and future directions.
So we have carried out this project with diabetes dataset, which has under 400 rows. The EDA and the ML models were done focusing on skin thickness and BMI. Hence, as an innovation, pharmacies can introduce pre-screening methods using skin thickness and BMI, since there is a positive correlation between these features. As the reflections of this project, the reliability of the dataset is limited because of the smaller and skewed dataset. This impacts the model, and the increase in outliers will eventually lead to possible overfitting. Hence, in the future, one can aim for a larger and representative dataset for smooth evaluation and to obtain more skills. However, in conclusion, as a takeaway, we as a team need to improve skills that facilitate addressing skewness and to remove additional outliers. So this would also be a future work for us to enhance the model performance. Thank you.
To summarize, we talked about the dataset, data processing, EDA, feature engineering, and models, innovation, reflections, and future directions. Thank you.